What's up, guys? My name's a knowledge expert, and today we are going to be doing some angular physics, right? Rotational physics problems, right? So let's do some rotational physics. All right. So our first question will be: we have two identical pucks that are laying flat on an icy surface, and both are pulled via a thin string by a hockey player. The hockey player pulls with the same constant horizontal force on both pucks for 2 seconds. Alright, so let's draw our two pucks here. So, there we go. They're two identical pucks, and it's the same constant horizontal force on both pucks for 2 seconds. But in the first scenario, the string is wound outside of the puck. So in the first scenario, we have a string that's going to be pulled like this around the puck, and here is going to be from the center. We are going to be pulling the puck right here from the center. Now, question A asks us which puck achieves a higher speed. So the key idea here is that linear momentum, which is delta P, is equal to force multiplied by time. Linear momentum depends only on force and time, not torque. So here, we're not going to be working with torque and that, because here we want to know what the linear momentum is. So the player pulls with the same force for the same time on both pucks. So we can know that both pucks will gain the same change in momentum. So delta V will be F delta T over mass, based on the equation that linear momentum is equal to m delta V. So it does not matter whether the puck spins or not. Spinning does not steal linear momentum. So therefore, both pucks have the same final speed, because we are not focusing on whether it spins or not. We are not focusing whether it rotates or which one. Here we only want to know about linear momentum. And spinning does not steal from linear momentum. So this was a bit of a trick question. So let's pass to the second one. So the answer to A is that both will have same final speed. Now for B, it says, in which scenario does the hockey player do more work as they pull on the string? So we'll have to use our equation for work, and we know that work is force times distance. So work depends on how far the point of contact travels. So in scenario 1, the string unwraps around the puck. That means the string must travel farther, right? Because the puck rotates while being pulled. So the same force, longer distance, more work. So the correct answer is in scenario 1. So this puck will have a more work as we pull on the string, because we do know it's the same force. The force is constant for both, but the distance for number 1 will be a bit longer because it rotates. All right, question number 2. Let's do question number 2. So, question number 2. You are sitting on a chair with the angular velocity shown with your arms pulled in your chest. Then you throw your arms outwards. Which graph illustrates your angular velocity during this action? Up as well. So of course you can't really understand what's going on here, so I'm just gonna draw it. So essentially you are like this, sitting on a sort of thing right now. You are sitting like this on a chair, and you have your arms curled up like this, and so your angular momentum will be like this. But after a while, you will have your arms completely stretched out with your weights. With your weights here. There you go, and you're sitting right here. And so we are given so which graph is the good one? So as you are spinning on a chair, arms in. So as you have your arms in, you will have a. So in this situation, initially, you will have a low moment of inertia. Your arms are in, and according to the moment of inertia, the equation, mr squared. And the r is pretty small. So the moment of inertia is pretty small. And because the moment of inertia is low, you'll have a fast spin. So the angular velocity will be bigger. And then because your arms are out, you'll have a bigger moment of inertia because r is bigger. And so you'll have a slower spin. And so because here we have a smaller moment of inertia in here, we can write the conservation. We can write the conservation of angular momentum using these two facts, right? And the way it equilibrates, because even though the moment of inertia got bigger, the angular velocity has gotten smaller. So of angular momentum, and we know there'll be L in with the arms in will be equal to L out, which we could write as the moment of inertia in times the angular velocity with the arms in, which is equal to, right? This is just rewriting the equation of angular momentum, which is this. So when you increase I, omega must decrease. So initially you will have, so the graph will be that initially you will have a, so the graph will look something like this. This is for angular velocity. This is the graph for angular velocity. It'll be constant, and then it grows a bit, and then it's constant again. So this is the answer for the graph of angular velocity, because it was constant, but then it will increase, so it can so it could be there. So it must be constant, and then it raises a bit, and then it is constant. Yeah, and so for number 3, for the number 3, we have a bear on a bicycle, a unicycle. So a bear wearing tactical goggles is riding a motorized unicycle as shown above. The radius of the wheel is r0.9 meters. So let's draw our big wheel here with radius r, which is 0.9 meters. and the initial angular velocity is 1.7 rad per second. The wheel has a mass of 5 kilograms. And we assume the mass is located on the outer of the wheel. So, yeah, so of course we have a hoop-like object, a hoop object essentially. So we know that the moment of inertia will be this. So the barrel accelerates the unicycle by supplying a net torque. Torque will be 4t squared Newton meters into the page for 2 seconds. So the moment of inertia is that way. It's in the page. So it is the final angular velocity of the wheel in rad per second. So we do have a torque that is applied for 2 seconds. And so we're trying to find the final angular velocity. What you can do is that you could use this equation. Torque times time is equal to the moment of inertia times the variation in the angular velocity. I was blinking, sorry. So this is the bit. How do we get this equation, right? Because we have torque is equal to I times angular acceleration, and you could write that as moment of inertia times varying angular velocity over time. And so you rearrange the patterns to get this equation, which can help us with our thing. And so we're just going to compute angular impulse. So this is angular impulse. So we're just going to put 4t squared, and then delta t is time 2, and then we're going to divide by the wheel's moment of inertia. And the moment of inertia of the wheel is going to be 5 times 0.9 squared. Okay. And so you're going to add with and you want to find this one. You're going to want to find because this is omega f minus omega I, and we know that omega I is given to be 1.7 rad per second. And so if you put everything here, the time, that is 2 seconds, and the torque, and if you just put all of it, because you have all the information you have, you should get final angular velocity to be 4.33 rad per second. So this should be final answer. All right. So let's pass to number 4. So we'll consider these. So you have 4 symmetrical objects above. Each object has a force exerted upwards on the left mass, and a force F exerted downwards to that, which mass has the greatest initial angular acceleration. So we have A. So we'll have a bunch of options. This is a multiple choice question. So this is 2R. And then B. This is of a mass m of a distance r. C is going to be of a distance 2r and the mass is 2m. And D is of a mass r, is of a distance r and of a mass 2m. And we want to know which object has the greatest initial angular acceleration. So here, what you're going to want to do is you want to use is this equation? The angular acceleration is equal to torque divided by the moment of inertia. So the torque will be the same in all cases, so torque will be constant. So the one with the smallest moment of inertia has the largest angular acceleration, because angular acceleration is directly proportional to 1 over I. And so I is mr squared. So the one with a very, very, very big r, will be very big moment of inertia. And so the one with a very smaller one, and so we could see that B here has a very small distance, has a very small radius between these two masses, and the mass is pretty small. So the moment of inertia is the smallest, and so because the moment of inertia is smaller, the angular acceleration will be bigger. So B is the correct answer. So I hope this helped for a couple questions in some rotational mechanics, a bit of physics. I hope this helped, and yeah, that's about it.